Hello children, in today's class we will be discussing what actually Oersted experiment and what are the observations of Oersted experiment. And children, examination point of view, these observations are very important. Then we discussed how to find the direction of magnetic field around the current carrying conductor. There we will be discussing about right hand thumb rule. Then we will discuss how the magnetic field pattern will be around the current carrying straight conductor. Then we will discuss the magnetic field pattern around the current carrying loop. It might be loop or it might be coil. So first let us discuss what actual Oersted experiment, children. Children, it happened in 1820. So children, I am saying that it happened means then only you can understand that it was not a pre-planned experiment. It was not a pre-planned experiment. So the scientist name called Oersted, he thought of doing something, but some other thing he discovered actually. So children, one day what happened, he went to the what we can say electricity lab, where he thought of conducting some experiments and activities with the simple electric circuits. But after entering into the electricity lab where he wanted to conduct the experiments with the simple circuits, he realized that in his pocket there was a magnetic needle. So then what he did, so instead of going back, of course he might be coming from the lab where he conducted the experiments based on the magnets and magnetism concepts. Okay now, so he didn't want to go back to the lab to keep that magnetic needle. So then what he did, just he placed that magnetic needle on the bench where he was conducting the experiment related to the simple electric circuits. So till that time everything was fine. And when he was conducting the experiment, he could notice, I can say he was shocked and he was surprised also. What happened? He could notice some deflections in magnetic needle. And generally children, we are sure, and he was very sure that magnetic needle was getting deflected, which means what? There would be some magnet. But he was very sure that it was an electricity lab where there was no magnet. But again he got doubt, might be placed somewhere else. So he started searching nearby him. He pulled the drawer of that bench, near the room, and once again even he checked in his pockets also, whether was there any magnet in his pocket. But he could not find any magnet. But still whenever he was doing experiment related to that simple electric circuits, he could find deflections in a magnetic needle. He was, what we can say, he was shocked and he was surprised, and he searched like anything. Maximum time he spent. Beginning he couldn't understand what was the reason why that magnetic needle was getting deflected. But after some days children, what happened, he got doubt actually. Still he was not sure what was the reason, but he got doubt. What was that doubt? So I was conducting experiment related to electricity and it was a magnetic needle. Was there any relation between the deflections of magnetic needle with this electric circuit? Then he started observing, then he started thinking, then he started conducting series of experiments. Then after so many series of experiments, children, he could come to the conclusion that the current which was passing, means how when he was conducting experiment, as long as the current is passing in that electric circuit only, the magnetic needle was getting deflected. Then he could conclude that the current which was passing through the conductor, through the wire, was responsible for the magnetic deflections in a magnetic needle. That is fine. But what way? It was the reason, children. So here, what happened? There only he concluded by saying that there would be a magnetic field around the current carrying conductor. For example, children, if it is a just imagine that it is a current carrying conductor. So current is passing through it either like this, vertical upwards or vertical downwards. That is second thing, that is. So then he said that so there would be a magnetic field around the current carrying conductor. Then we may get one doubt. Of course, it happened like that. Okay, na? Means he proved that there would be a magnetic field around the current carrying conductor. But how we will come to know that? It's very simple. Just take a magnetic compass, and just place near any current carrying conductor, and obviously you will notice, we will notice that there will be some deflections in a magnetic needle, which shows that yes, there is a presence of magnetic field. There is a presence of magnetic field. So now let us try to list out some observations made by the Oersted. Children, for suppose here let us consider simple electric circuit. So here two we have considered. Let us see why we have considered two simple electric circuits. Why not only one? Let us see here, children. First, children, in this case, let us say this switch is on. Right, this switch is on. So which means what here? When you on the switch, obviously there will be a current and always from positive terminal to negative terminal. So this is how current will pass. Okay, na? That is fine. And children, what is observed? What is observed is that whenever current is passing through the conductor, now in this case current is passing from A to B. So according to Oersted experiment, there will be a magnetic field around the current carrying conductor. Fine. Then what is evidence? Yes, this magnetic needle will get deflected. Children, especially here, very important. We will observe the direction of North Pole here. Why only North Pole? Children, here we know that monopoles do not exist. Monopoles do not exist. So always poles, North and South Pole will exist as a pair only. But just let us imagine situation. If monopoles would exist, imagine just, it's not at all possible. Of course, if imagination, anything is possible. So just you think that North Pole would exist. When you place North Pole in a magnetic field, so in which direction it would move? It would move in the direction of magnetic field. It's very important. If North Pole would exist individually, then it always would move in the direction of magnetic field. This is very important. Means with the deflection of North Pole only we can understand the actual direction of magnetic field. So in this case, it is noticed that, so when current is passing from A to B, it is noticed that this North Pole gets deflected in this direction. North Pole gets deflection. It is a North Pole, just think it gets deflected like this. It gets deflected like this, which means what here? When current is passing from A to B, magnetic field will be in this direction. Magnetic field will be in this. Of course, with this, it's clear that there is a presence of magnetic field around the current carrying conductor. Now, that is the first one, very important. So, what is the first conclusion of Oersted experiment? Around it. So children, this is a first observation it is. That is, current carrying conductor produces magnetic field. That's fine. And here children, now let us see in this case here. Now let us on the switch. But now what will the current direction? You can't say that it's A to B always. No, because here the terminals are changed. So it is from B to A. Means here we changed the direction of current. Children, when we change the direction of current, it is noticed that here the North Pole of the magnetic needle getting deflected in this direction. Which means what? So now the field direction is in this direction. So children, the first one, what is the first one? Current carrying conductor produces magnetic field around it. And what is the second point here? When you change the direction of current, magnetic field direction also changed. When we reverse the direction of current, children, so magnetic field direction also reverse. It's very important. In exam they will ask you, how can we change the direction of magnetic field? It's simple, by reversing or by changing the direction of current. So here the direction of current. So children, the direction of magnetic field is reversed by reversing the direction of current. This is the second observation. And children, now what we do is that actually, instead of this cell, let us take a battery. And even let us try to, what we can say, arrange the rheostat. So children, what is the purpose of rheostat, children? So with the help of rheostat, we can change the magnitude of the current. I mean, we can increase the current, we can decrease the current. So children, let us say here, for example, just example only, let us say that in this circuit, in the two situations, once we are sending 5 ampere current and next we are sending 20 amperes of current. So what differences we can notice? What changes we notice actually, children? Children, when we send 5 amperes current, children, it is really a huge amount of currents only. Just let us assume that here. So first 5 amperes current is passed. Let us say 5 amperes current is passing the circuit. Then we notice that of course magnet gets deflected in this direction only, but we will notice that it deflects very slowly. It deflects very slowly. Okay now. Whereas when we increase the current to 20 amperes, then we notice that magnet will get deflected very fast manner, very fast. Which means what, children? When we increase the current, the deflections are becoming more in a faster manner. Which means what here? The magnetic field around the current carrying conductor also increasing. It's very important. Means what here? By increasing the amount of current in the circuit, children, we can increase the magnetic field strength around the current carrying conductor. So that is the third conclusion. What is third conclusion? By increasing field is increased. So it's very simple. So the direction and the magnitude of the magnetic field, children, can be changed by reversing the direction of current and even by changing either by increasing or by decreasing the amount of current in the circuit. So these are the simple observation made by the actually Oersted experiment, what we can notice also, children. That is fine. But examination point of view, very particularly they will ask about the deflections of the magnetic needle when it is placed near the current carrying conductor. Here near means we will get a one doubt. Near means, see here we are discussing by keeping side. Near means what here? For example, it is a current carrying conductor. So what happens when magnet is placed above the current carrying conductor? And what happens when a magnet needle is placed below current carrying conductor? I mean what? In which direction is a magnetic needle get deflected? It's a very important. Children, now we will see in detail. Children, one more thing also very important. What is that actually? If there is no current in the circuit, then do we notice any deflections in magnetic needle? No chance at all. Means when current is present, there will be a magnetic field around the current carrying conductor and there will be some deflections. Okay, children. Now in detail let us see how particularly the north pole. Children, again I am telling you, whenever we are noticing the deflections in magnetic needle means what? You should keep in your mind that the north pole of the magnetic needle, in which direction it gets deflected. So that will be the direction of magnetic field. Children, it's very important. See, generally whenever we talk about the current direction means what? So direction of flow of positive charges. And a magnetic field means what? If what mono north pole would exist, so that would move in a particular direction. That would be the magnetic field direction. Okay, fine. Now we will see the how the deflections will take place in detail. So south, and here is west, and here is east. Now children, so here let us have 4 cases. So here diagram size is increasing. So it's not like that. We have taken 4 identical magnetic needles. 4 identical magnetic needles we have taken. Children, try to understand here. One important thing first we have to notice here. In the first 2 cases, try to understand magnetic needle is placed above the current carrying conductor. Which means what here? If it is like a current carrying conductor, either current is flowing from left to right or right to left, whatever it may be. So needle is placed above this. So here in these two cases, so above the current carrying conductor, so magnetic needle conductor. Whereas in these two cases, the magnetic needle is placed below the current carrying conductor. I mean, if conductor is like this, okay, it is placed below it. Try to understand, so below it. So in these two cases, magnetic needle is placed below the conductor. Now we will see how the magnetic needle gets deflected. Children, so actually don't think that these 3 are simplifiers. No, these 3 are the part of electric circuit. So like this. So you have to imagine that these three are also connected like this, as shown in the figure here. Okay, fine. In the first case, dear children, in the first case, try to understand here. In the first case, in which direction is the current is flowing here? Just compare with this, so that you will get idea here. So in a conductor, current is flowing from south to north. Then it is noticed that, dear children, this is what actually north pole of the magnetic needle. North pole of the magnetic needle is getting deflected towards, look at here, towards what? East. Towards east it is getting deflected. Very important. So whenever current is flowing in the conductor from south to north, such a way that needle is placed above the current carrying conductor, then north pole of the magnetic needle gets deflected towards east. This is a very important point, children. Then how can we remember? Yes, for this we have a small clue. That is the one word we have. This is snow rule. Actually, we can call it a snow rule. Children, there is no like a scientific snow rule. Snow rule is not a like scientific one actually. So it is a word, or it is a point to remember easily here. It's very important. So look at here. Just compare with this. So current is flowing from where to where? South to north. Okay. Current is flowing from south to north, and over it magnetic needle is placed. Over the current carrying conductor, magnetic needle is placed. Over what? Over the current carrying conductor, magnetic needle is placed. Then here, what happens here? Oh, sorry, I think I said wrong here. It is not east. Sorry. So it is deflected towards west. It is deflected towards west. So it's not east. It is not east. It is a west. So that is you can see here how this snow rule is working out. So children, whenever current is flowing from south to north in the conductor, and even what we can say magnet is placed over the current carrying conductor, then the north pole of the magnetic needle gets deflected towards west. Children, very important. I repeat once again. When current is flowing from south to north and a magnetic needle is placed over the current carrying conductor, then north pole of the magnetic needle gets deflected towards west. So this we can remember with the help of snow. Children, once you know this one case, then other three cases will be very simple and easy. Very simple and easy. How? Look at here. Now children, by changing the terminals of the battery, we can reverse the direction of current. So let us say in the same case only, but current is flowing from north to south, not south to north. Current is flowing from north to south. Then what happens? So already we know that when we reverse the current direction, definitely magnetic field direction also reverse. So with that, you know, the north pole of the magnetic needle, children, gets deflected towards west. Very important. Towards east. Children, it's very important. When current is flowing from south to north, the north pole of the magnetic needle is getting deflected towards west. Whereas when a current is flowing from north, now what actually before south to north, now it is a north to south. Then the north pole of the magnetic needle is getting deflected towards east. And in these two cases, the same current direction we are going to maintain respectively, but the magnetic needle is placed below the current carrying. Let us this current carrying conductor. Now magnetic needle is placed below the current carrying conductor. Children, let us see here. Now in the first case, how? In the first case, the conductor is connected in the circuit. Similarly, here also it is connected. Which means what here? The current is flowing from south to north, like in the first case. This is a current direction. Then in this case, it is noticed that the north pole of the magnetic needle is getting deflected towards east. So don't get confused. Here magnetic needle is placed over the current carrying conductor, above the current carrying conductor. Here magnetic needle is placed below the current carrying conductor, and the current direction is south to north. Then north pole of the magnetic needle gets deflected towards east, and this is quite opposite. Now let us reverse the direction of current. That is what? Current is flowing from north to south. If current is flowing from north to south, then it is noticed that the magnetic needle gets deflected towards west, So children, these are the observations how magnetic needle gets deflected. So when a magnetic compass is placed above the current carrying conductor, and here magnetic needle is placed below the current carrying conductor. Here two cases we have. Again in that also we are reversing the directions. So when we reverse the direction of current, children, obviously the magnetic needle, what we can say, deflections also will be reversed. So this is all about Oersted experiment. Children, 3 points which you have to remember, very important thing. The first point, actually, this experiment would prove that current carrying conductor produces magnetic field around it, first point. And where the second one is that here by reversing the direction of current, we can reverse the direction of magnetic field, and by increasing or by decreasing the amount of current in the conductor, children, we can either increase the strength of the magnetic field or we can decrease the strength of the magnetic field around the current carrying conductor. But children, there will be one question. Okay, this experiment proved that there would be a magnetic field, and we all know that magnetic field is a vector quantity. Means what? We should know the direction here. Of course, here it's okay, very clear. Here how the based on this north pole deflection, we'll come to know that. For example, here if current is passing through this conductor, so no doubt about it, the current will be around this current carrying conductor. But in which direction? Whether it is a clockwise direction or anti-clockwise direction. So how can we come to know that the direction of magnetic field around the current carrying conductor? Children, for this the answer is given by right hand thumb rule. Let us learn about right hand. Children, when you are okay with this right hand thumb rule, children, then you can find out the direction of magnetic field around the current carrying loop. It's very important, very important. So here right hand thumb rule is going to play a very important role to understand how can we decide the polarity of the current carrying loop, current carrying what we can say, coil. So let us discuss that now. Children, in examination they will ask you, it's a direct question. So what is that rule? What is the rule which is used to find the direction of magnetic field around the current carrying conductor? State that rule. So directly they will ask you, means they will not ask you state right hand thumb rule. No, they will ask you what is that rule is used to find the direction of magnetic field around the current carrying conductor. So let us write what is the use of right hand thumb rule, dear children. So current carrying conductor. It's very simple. So children, here what actually right hand thumb rule is that? For example, children, let us assume that it is a current carrying conductor. Now you think that the current is, what is first we should know the direction of current. So let us assume in this current carrying conductor, let us assume that current is entering through like this and current is leaving through tip, means vertical upwards. So now what we have to do, let us assume that this current carrying conductor is held with right hand. I am going to hold this current carrying conductor with right hand. Now see in which direction my thumb is, children? Upward, which means what here? Current is flowing in this direction only, my thumb also showing in this direction, which means what here? My thumb is showing the direction of current. If my right hand thumb shows the direction of current, and look at here, to hold this, I have to curl these fingers like this. I have to close, enclose. These fingers should be enclosed like this. So the direction in which these 4 fingers are closed will be the direction of magnetic field. Children, imagine, come on, just start. Children, let us take a pen and try to hold with your right hand. Then only you can understand. Children, here magnetism, complete this concept is invisible. You have to imagine, you have to assume the situation, then only you can understand easily. Come on, let us start. Take a pen, try to hold with your right hand. Come on, start doing. So it's a right hand you are holding this. For example, children, let me keep your right hand like what we can say pen like this. Sorry, it is not pen now, it is a current carrying conductor. How the current is flowing? Now current is coming like this. Current is coming towards you all like this, towards camera the current is coming. Now I am holding like this. So my thumb is showing the direction of current, and in which direction I am curling the fingers, children? For you it is anti-clockwise. Anti-clockwise means if current is coming out of the board, then magnetic field is anti-clockwise direction. Whereas if the current carrying conductor is held like this, now what is happening here? Current is entering into the board, children, into the board. Now I am holding the current carrying conductor with my right hand. Try to understand, right hand here. So now my thumb is showing in this direction, but in which direction the fingers are closed here? Now for you it is clockwise direction. Means if current is entering into the board, for you into the board, then magnetic field around this is clockwise direction. If it is coming out of the board, then magnetic field is anti-clockwise direction. Children, very, very simple. If it is like this, whatever may be the direction here, okay? So simple, it's very easy to identify the direction of magnetic field with the help of right hand thumb rule. Now children, here, look at here. Fine. So then how can we state the right hand thumb rule? So just assume the situation that the current carrying conductor is held with right hand. If thumb shows the direction of current, then the four fingers in which direction you are closing will be the direction of magnetic field. Very, 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 very simple. And children, even in exam, they may ask you which law is used to find the direction of magnetic field around the current carrying conductor, and state that law. And even they will ask us to draw at least 3 magnetic field lines around current carrying conductor. So look at here, children. So let us take here. So for sake of our comfort, let us take a thick wire. It's comfort only. This for sake of our comfort. This is okay. Now fine. Now here let us take here one more current carrying conductor, because we know that when we reverse the direction of current, the magnetic field also reversed. So children, first here, so to get that 3D field, just that's it. So just I drew 3 magnetic field lines. Narayana, excuse me. Fine. Let us say it is this one. Children, here, okay, anyone can draw this circles, it's simple only, but the thing is that the direction is very, very important. Children, as we know that, for example, in this, the current is flowing like this. This is a direction of current, children. If current is flowing in this direction, means come on, start. Let us use right hand. So this is, just imagine, children. So the 2D figure, just we need is imagination. So conductor is like this. So current is flowing like this. Then magnetic field lines are, if you are noticing from top like this, then how the magnetic field lines are? Clockwise direction. So this is how actually magnetic field lines will be. But whereas here, let us reverse the direction of current in this. Yes, it is in our hand only. By changing the terminals of the battery, we can reverse the direction of current. It is not that much big task. Okay, now. So here what will happen, dear children? Now current is flowing, conductor is in this direction. So like this. Okay, now. So now like this. Now field lines are like this. Just try to notice in which direction I am closing my 4 fingers. So they are clockwise direction. Means like this, children. So this is right hand thumb rule. Children, what is the purpose of right hand thumb rule? So with the help of right hand thumb rule, we will find the direction of magnetic field around the current carrying conductor. So state the right hand thumb rule. So we are holding just assume that the current carrying conductor is held with the right hand. If thumb shows the direction of current, then the fingers in which direction we are closing will give the direction of magnetic field. So this is all about right hand thumb rule. Now children, we will see how the magnetic field lines, how the magnetic field pattern will be around the current carrying state conductor. So magnetic field around the straight current carrying conductor. And children, for this a small activity is there. Look at here. So children, this is a arrangement setup actually, and this is cardboard. It's a cardboard, and here AB is our current carrying conductor, is connected as shown in figure. And children, just you try to understand, it is like, if it is like, current carrying conductor. For example, let me take a textbook here. So sorry, it is a cardboard. It's a cardboard. So perpendicular like this, the current carrying is passing perpendicularly. Okay, now. So just that is how we have to imagine. And children, here over this what we can say cardboard, so iron filings are sprinkled here and there. They are randomly they are sprinkled. There is no order. Just we sprinkle like this. Okay, now if switch is on, then what will happen? Obviously, current start flowing in this direction. Current start flowing in this direction. But try to understand in which direction the current is flowing in the conductor. So now A to B, if you can see, the current is flowing, children, A to B. This is a very important. Current is flowing from A to B and like this. Now children, we notice that, so whenever there is a current in the conductor, and it is noticed that the iron filings which are sprinkled on that cardboard, they'll get adjusted. They'll get adjusted in a particular pattern. They'll get adjusted in a, like a circles, that too concentric circles, concentric circles. So this is how actually the magnetic, what we can, this one, iron filings get adjusted. So here, which represents what actually? Magnetic field lines, which represents actually magnetic field lines. But the question is that, how these magnetic field lines are? Of course, the first point is very important. The magnetic field around the current carrying conductor or concentric circle. Children, it's very important. So here, magnetic field lines around the conductor, that is a straight conductor only, or concentric circles. Children, what are concentric circles here? The circles which have same center, same common center. For all circles, the center is common only. Okay, now you can notice it for this center is here only. Means the center is lying, the center of all circles is lying on the axis, on the current carrying conductor only. But in which direction the magnetic field is very important. How can we find out that actually? By using, come on, right hand thumb rule. Now how the current is flowing, children? In the direction of current, try to understand here. So thumb should be downward direction. So now you have to imagine like this. This is how actually we have to fold our finger. So if the current is flowing vertically downward, children, then you are observing from top. Let us think like this. You are observing from top. Then you are curling your fingers in clockwise direction. So here the magnetic field lines are clockwise direction. Very simple. What happens when you reverse the direction of current? Obviously, magnetic field direction also reversed. Then we will get in an anti-clockwise direction in that case. Okay, na? So first point, children, here. So the magnetic field lines around the current carrying conductor are concentric circles. And if the current is flowing vertically downward direction, the magnetic field is clockwise direction. If the current is flowing vertically upward direction, then the magnetic field is anti-clockwise direction. And children, with the help of rheostat, we can increase the current, we can decrease the current. For example, children, we are increasing the current. Then we know that when we increase the current, the magnetic field strength also increases. But how we will come to know that? Because magnetic field is invisible. Then how we will come to know that? Children, the moment when we increase the current, we will notice that the magnetic field lines will become very closer. Will come to very close. Means the density of the magnetic field lines increases. As the density of the magnetic field lines increase means what? The strength of the magnetic field also increases. Okay, children. So this is the how magnetic field lines will be around the current carrying straight conductor. So children, in our today's session, we discuss what actually Oersted experiment and observations, and various cases we discussed under the Oersted experiment, and then we discuss the right hand thumb rule, and even we discuss how the magnetic field will be around the current carrying straight conductor. In the next session, we will be discussing how magnetic field will be around the current carrying loop, and there we discuss about solenoid and electromagnet. Children, so we have to discuss in line actually magnetic field around the current carrying loop, solenoid and electromagnet, then only it will become very easy. So actually children, so due to the technical issues we could not upload the videos regularly. So now onwards we will be uploading the videos regularly so that you can follow and you can learn. Thank you so much. All the very best.